Hello. It is a series lecture of solid-state physics. From now on, we will talk about electronic transport properties. And the chapter 10 is the energy band structure. Yeah, chapter 10 is energy band. We know that in quantum mechanics, we consider four single particles, and the single particle problem, there is a quantized energy, especially for hydrogen atom. Hydrogen atom have a quantized energy. It is energy is not continuous, but discontinuous as quantized energy level. But in solid state, there are so many ions, so many lattices, and each ion has many electrons and atomic. When we close with each other, and the overlap of the energy band makes the energy level. The overlap of energy bands, energy level, which makes the energy band structure. Basically, the origin we will discuss for the origin of the energy band structure, and the important factor in solid state is the periodic potential. It means that translation symmetry, and the translation symmetry is very important factor in solid state. Here I will start from the Bloch function. Here we consider for periodic one-dimensional lattice. Periodic lattice in one-dimensional. Is the representative picture for the periodic lattice in one-dimensional structure. Here the ions reside at periodic lattices and the ionic we consider for the potential, and the red one is a potential. Potential has a negative potential in the vicinity of the ions, and the potential is very periodic in one-dimensional. Then if the periodicity of potential is A, and the potential is that R plus A, here the in this case it is a one-dimensional case, and this vector representation is a three-dimensional analog, and therefore here the A vector is equal to the reciprocal Bravais lattice vector, and it is Bravais lattice vector. And it can be generalized in three-dimensional case. Here we adopt the independent electron approximation because in solids so many electrons, and we cannot consider for so many electrons in solids whether it is not necessary, and we just only we need only one electron. One electron represent all the electrons. We can understood like this, and in a crowd, and there are so many people in a crowd, like subway, and so there were in subway station in New York or Seoul, and so many people crowds and moves around, but each people has an individual character, but we do not consider each characteristic persons, but every person has the same characteristic. There are humans, therefore, then the one people can represent all the people, and therefore that's why the so many crowds, and the people cannot interact with each other. And in a small group, small group can interaction become strong, And for example, when we have a meeting and when we have a discussion, it is correlated with each other, and also there is interaction. But in crowds, whether in subway station and in individual people cannot do not interact with each other. In that case, we can think about that it is one person have a representative of all the other persons. Here we therefore electrons is like this. Therefore, we call it is independent electron approximation. Independent electron approximation says that many electrons do not interact with each other. And one electron represents of all the electron system. Therefore, in this case, we should think about that we should solve the Schrödinger equation of a single electron. This independent electron approximation is very simple approximation and very effective. And from the Schrödinger equation, H psi is that kinetic energy term, H bar square, del square plus potential. Psi represent for the eigenvalue epsilon psi. Here in this case, the potential is periodic. Potential is periodic, that VR is that VR plus R, and capital R represent the Bravais lattice vector. This wave function, because the potential is periodic, and the electronic wave function should also have the periodic. Then therefore, the wave function should satisfy the periodic translational symmetry. Because when you think about that, the periodic lattices like this, and the potential is periodic, it is negative potential, and this potential is very periodic, and the electron wave function is periodic because electrons in ions are localized and localized. But in this case, then the electrons have an extended state in the above the ions, because there are two electrons. One is that co-electron. Co-electron is bound to the ions, and the itinerant electrons flows from the atom to the other atoms, and which flows the electron. But in wave function also should satisfy the periodic boundary condition, and therefore in this case, and the wave function can have the form like this, and the nkr should have the exponential ik dot r and the unkr. It is very important because this exponential function represents a plane wave, because exponential ik dot r represent the cosine plus I sine. Therefore, it is periodic and plane wave extended state. And also here U function is the wave function near the atoms. There are two quantum numbers, and the one quantum number is n, and the other one is that k vector. And vector r represent it is displacement, and it is n is a quantum number. And in ionic potential, there is a quantized energy level. Therefore, n should consider the quantum number. And k is the wave vector, because in a wave there is a wave. We can define the wave vector. Therefore, this wave function have the form that wave function near atoms, and this wave function has an extended state with a plane wave. Therefore, this psi have a representation for the exponential IKR U function. Therefore, it is very important to be considered. It should satisfy the periodic boundary condition or the periodic potential. And therefore, the atomic wave function should have the periodic condition. Therefore, U and K R should satisfy that U and K and R plus R, because it is there is a translational symmetry. Therefore, from these above equations, and the psi and k r plus r should satisfy that the exponential I k dot r and the psi and k r. It is you can simply understood that this wave function, if we define that the wave function is a plane wave state of the atomic wave function, then it is there is a periodic boundary condition of the translation symmetry, and therefore here the exponential I k dot r represent this r represent Bravais lattice vector, and it is very important. We call it is a Bloch function, Bloch theorem. Bloch theorem, whether this wave function is a Bloch wave function. Here, this Bloch wave function means that the wave function in the periodic potential, and we only consider for the one-dimensional lattice, but it is not restricted in the one-dimensional, but it can be extended to the three-dimensional space. And therefore, then Bloch wave function is a basic wave function in solid state with translational symmetry. Secondly, the Schrödinger equation with this Bloch wave function is very important. We call it as a central equation, and here we consider for Schrödinger equation. In momentum space, we call it as a central equation. And actually, in previous lecture and structural properties of solid, I talk about that because the ionic solid state is very ionic spacing is very small. We cannot observe the ionic lattices, whether atoms, but in real space there is a real space and momentum space, and practically we observe the solids by the diffraction experiment, like electron diffraction, X-ray diffraction, or the neutron diffraction. And basically the diffraction theory follows the Fourier series in mathematical form. Therefore, here we only consider for the momentum space in not real space, because in solid state, the crystal structure and unit cell is very small, and it is very difficult to observe in real space. Then therefore we only consider in momentum space, and the measurement itself is a Fourier transform of waves, scattered waves. Therefore, in Schrödinger equation, real space also should make the momentum space equation. And here, the real space potential can make a Fourier transform. Fourier transform of periodic potential can have a represent like this, and here there is a potential has the potential resides at the Bravais lattice, because ions have the negative potential. Therefore, ions forms a Bravais lattice in a solid. Therefore, the potential have a Bravais lattice component, and also exponential I g dot r is the Fourier transform extended state, and also it is not integral but summation with respect to the reciprocal lattice vectors, because this reciprocal lattice vector is not continuous, because ionic solid is not continuous but discrete. It forms a crystal structure. Therefore, the summation g not integral means that lattice vector summation are not continuous but discrete Bravais lattice. Here, the wave function also has the extended state. Therefore, Ck means that there is an amplitude of the relating to the atomic potential. It's exponential I k dot r. Here, the summation for the k vector. Summation with k vector represent the r vector here, and also because there is a periodic potential requirement. Therefore, here r vector should follow that periodic potential. Here n plus ni ai. We call it is Born-Kármán boundary condition, and it means that the solid can think about like a chain. For example, like this chain structure, and it is 1, 2, 3, blah blah blah, and n and n minus 1, and the atomic wave function for r1, it is equal to atomic wave function represent for the lattice spacing equal to a, then plus n a. It is identical with each other. Therefore, it is a periodic boundary condition. Periodic boundary condition with a single chain, we call it is a Born-Kármán boundary condition, and it is very natural to understood. It is one-dimensional. It is also can be considered as a one-dimensional lattice, but it also extended to three-dimensional space, because in three-dimensional space we know that the three-dimensional space can be extended in the two-dimensional by cutting some pieces. Then we can think about that three-dimensional. For example, if it is a cubic structure, And the cubic structure can be extended like this, and there are three faces like this. 1, 2, 1, 2, 3, like this. Anyway, 1, 2, yeah, okay. Then we can make this kind of from this from the starting point, and we can make a 1, 2, 3, 4 like this, and we can make a single line like this. Anyway, then we can make a single line, and the three-dimensional space can transform as a one-dimensional lattice. Therefore, in real lattices and also upon Kalman boundary condition, suppose that in n atoms and n nearest neighbors, nth nearest neighbors have a same particle from the starting point, and it is a von Karman boundary condition. It is natural to understood. And here, from the Schrödinger equation, and the Schrödinger equation say that I will write again. It is minus VR psi equal to epsilon psi, and because when you suppose that the wave function should satisfy this this form, and the second derivative with a real space, it means that minus k square. Therefore, from the first term, minus k square becomes for k summation, and h bar square k square over 2m ck exponential I k dot r. It is a kinetic energy term, and the potential energy and the real space potential energy has this kind of reciprocal lattice representation, and therefore reciprocal lattice vector and the Vg exponential I k dot r and also the psi and the k ck exponential I k dot r, and the energy is that energy summation k ck exponential I k dot r. Here let's consider this potential term. We call it as a star, and let's start from the star. It is a real space potential and psi. Then summation for reciprocal lattice vector and the wave vector, and the Vg and ck exponential I here I k plus g, because from the boundary condition we can from the Bloch wave function and this vector r vector can have the reciprocal lattice vector, and therefore here k this reciprocal lattice vector and the g vector, it is a g, not k, but it is g dot r. Here let's denote that it is a k prime. Then k prime is that k plus g. Therefore, k is that k prime minus g. Then this potential has the summation for g, summation for, actually it is a k prime. It is k prime and the Vg and the c k equal to becomes k prime minus g and exponential I k prime dot r. But this prime can be omitted because k prime and k is similar with identical with each other, and therefore this k prime can we can eliminate the prime. Therefore, when we substitute this equation in the original equation, and summation for k h bar square k square over 2m ck exponential I k dot r and plus this potential term becomes like a reciprocal lattice vector and wave vector Vg and the c k minus g exponential I k dot r equal to energy and summation k ck exponential I k dot r. Therefore, and the summation for k exponential I k dot r, it can extract it in the outside, and here h bar square over k square over 2m minus energy and ck, and the potential energy term is that summation for g and the Vg c k minus g equal to 0. Yeah. Therefore, because this plane wave function is not 0, therefore this term h bar square k square over 2m minus energy ck plus summation g Vg c k minus g equal to 0. And we call it as a central equation. We should remember this equation. It is the Schrödinger equation in momentum space, and it comes out from the Schrödinger in real space Schrödinger equation. We call it as a central equation. It comes from the momentum Fourier transform of the real space Schrödinger equation. It is momentum space Schrödinger equation. Therefore, and from now on, we will consider for this central equation, not Schrödinger equation in solid state, because the periodic condition is very important. And also, let's think about that. We can show that this central equation should follow the Blocher theorem. And the Blocher theorem means that this equation, the solution of this equation should satisfy the Blocher theorem and the periodic boundary condition. Therefore, here let Q vector is in the first Brillouin zone. Brillouin zone means that it is a K space is plus minus, it is within the pi of A. A is the lattice spacing, and it is first Brillouin zone. Then here K momentum, electron momentum has the K minus G prime, and here G prime means that another reciprocal lattice vector, and because the lattice is periodic, and the translation of the reciprocal lattice vector is identical with the original lattices. Therefore, the K vector and the Q vector is the same electronic wave vector, but Q is the different wave vector between K, but the reciprocal lattice vector minus or the plus also can be possible. And anyway, it means that the translation of the reciprocal lattice vector and it is identical with each other. Therefore, let's denote that K is that Q minus G prime. Then from the central equation, it means that the translation with reciprocal lattice vector. Because and the translation is identical, it should follow that the same result, h bar square over 2m and the q minus g prime square minus energy. See, k becomes that the q minus g prime and plus summation g vg, and k is that q minus g prime and minus g equal to 0. Here let's denote that from here, let's the g2 prime is that g prime plus g prime. Then we can represent that g2 prime. Therefore, here this equation h bar square over 2m and q minus g prime square minus energy and c q minus g prime plus summation for g2 prime, and here g is that g2 prime minus g prime, and also c q minus g2 prime equal to 0. Then it is same way that the k is that q minus g, and the g and g prime is can be different. Then here from this equation say that identical form, and the translation of the reciprocal lattice vector shows that the same Schrödinger equation or the central equation. And let's think about that wave function, and q vector with q vector wave function should follow that here reciprocal lattice vector and c q minus g, because k equal to q minus g, and the exponential ik is that q minus g dot r. Then it is that because exponential I q dot r is not irrespective with the summation for g, and therefore c q minus g exponential minus I g dot r. It means that it is the exponential I q dot r, and also this equation, it is the atomic wave function q r. Therefore, it satisfies the Bloch theorem. And therefore, in this case, we should remember that the central equation, and the central equation is important for solving the Schrödinger equation in the periodic lattice.